So, good morning, everybody. Let's continue with our signals and systems class today by studying discrete time signals. Until today, we were studying mainly continuous time signals, right? Let's get connected. So, guys, remember, we were really talking about until here. So discrete time, let me put the title as discrete time signals. So we have to make this distinction. Actually, as computer engineers, you guys may be more used to with discrete time signal. Discrete time signal is really just a sequence of numbers in a way, but we will look at where it's coming from. A sequence of numbers indexed by some time integer. In this class, it's time integer. For an image, it's space, integer or indices, or it could be multidimensional data. Some of you were saying this is really related to data science, data processing. You could be working at a company, company logs, customer logs, measurements. They are all signals for you, okay? And you guys now know all of those signals have frequency content. You can look at actually decompose at least your signal, project your signal onto different basis functions and look at important components in the signal. And in this course, we are looking at a very specific but very much important basis functions, which is Fourier basis. Currently, we're studying, until last week, we studied continuous time Fourier series decomposition. Today, we will look at discrete time Fourier series decomposition, okay? So a sequence of numbers, let's say, again, I know because we are computer engineers, we are used to working with arrays, vectors, matrices. This sounds good, but the mathematics, interestingly, gets a little bit more trickier when we go from continuous time to discrete time. So in terms of math, guys, I typically like to start with continuous time. I like to work continuous time. Things are neat, more elegant mathematically, but we have to know how to move to the discrete time. And of course, in our field, as a computer scientist, we have to really know how to implement these things numerically, right? For you, for instance, FFT, fast Fourier transform, is something that you will use a lot in this course and also later to form spectrogram of a signal, for instance, to analyze the frequency content in a signal and use it as a feature, for instance. A sequence of numbers indexed by integers, okay, or by an integer variable n, let's say, by integers, but here an integer, it's 1D signal, of course. For a 1D signal, it's an integer variable n, let's say. Here, in this case, it's 1D, right? This is 1D. Discrete time, we make it short by dt. So a signal representation, I can say, could be, I think we are mostly used to this graph, I can call it pictorial or graph representation, graph signal representation. And maybe also recall, we were mainly studying T, continuous time until here. Maybe just make it not just sinusoid, but addition of sinusoids. Now you guys know when you see such a signal, you can really write it as addition of sinusoids. It will become actually more general when we study Fourier transform. But sampling here, we want to obtain a sample signal. We want to obtain a sampled signal. Sampling is for us really taking every other sample with some fixed intervals actually. So really you have to know, let's say you have to say a sample signal, take every TS samples. TS is in seconds, that's my sampling period, okay? This is sampling period. So I would be like really, let's say, I'm sampling the signal, so like this. So this would be really TS, right? TS, 2TS, 3TS, 4TS, for instance. Let's say this was 5TS. Okay, I think it's clear. And of course, it goes, however the extent of the signal, however much it goes to. So this is really what is happening. But a sampled signal is really, this is still in continuous time axis, you see. These samples, red samples, we take it to a new graph, actually, for a discrete time graph, remember. This was x of t, guys. So now we go to an x of n graph. Maybe we've done it before, but let's, because we're studying discrete time signals, let's repeat this. I take it to a new graph like this. I mean, it has to be the same samples, but of course, I'm just really doing it roughly here, okay? I think you get the point, right? Guys. And it goes up again. I think it's clear. I mean, these are your samples of the sampled signal. Okay, and now these are indices here. Important thing is, let's say we have to have, 0 was here, sorry, okay, let's start with, I mean, the axis was drawn here, so should be fine. This was 0 here, now 0, 1, 2, 3, 4, 5. Okay, you guys, I think, see what is going on. Let's say this was it, -3. Anyways, so this x of n, let's say, is a sample signal. This is my sample signal, let's say. For a generic signal like this, I can write it or show it pictorially like this. I can also have a functional representation. For instance, if the signal was something like this, let's call maybe, let's just give an example. I can have discrete time signals like this. It's an exponential discrete time signal. Here it's a decreasing one. For instance, this guy pictorially would be really starting from 1, goes to 1/2 at index 1, right? And it should really go to 1/4 and move on like that, 1/8. And you see it says this envelope actually, but it's really just these samples. This would be the discrete time signal, this x of n, but it has a mathematical representation like this. We can also tabulate this, guys. So I mean, this is, I think, what we are used to, tabular representation. This was mathematical or functional. And I can tabularly just tabulate and say n and x of n, sorry, x of n, let's say, okay, let's do it like this. Maybe wherever it starts from, -2, -1, 0, 1, 2, 3, and just have to, this was 0 for n less than 0, so it was 0 on the left-hand side, and it starts as 1, 1/2, 1/4, 1/8, right? So that would be it. And for us, actually, I was saying, computer engineers, it's a sequence or array. So, or if it's multidimensional, it's matrix, tensor, right? It's the same thing. It's the 1D is really, you can maybe just say, I can represent it in this way, okay? So for instance, you have to here just note where n is 0, however. You have to know the corresponding time axis. So this is just a very simple introduction to what a discrete time signal is. There are some elementary discrete time signals, like a unit step, delta, impulse. Elementary discrete time signals. Let's just know what they are. We also use their continuous time counterparts, you guys will see. For instance, I can have, again, this more general exponential sequence, alpha to the power, and typically for us, I mean, it could be the other way around, but alpha is between 0 and 1. If it's alpha, I mean, alpha is greater than 1 is also possible, of course. The equivalent, maybe just the alpha between 0 and 1 is e to the minus at type, right? So a e to the minus at type. Okay, so it's really like this guy is alpha here, a positive, remember. This is like R. I mean, this is really A e to the minus AT signal. I mean, this is the continuous time version, okay? It's continuous time version. Alpha greater than 1, I can just say it's a growing exponential, right? So for instance, it is 1 and whatever alpha is, of course, this is alpha, alpha square, etc. Continues like this way. It could be 0 on the other hand. Okay, so now I have also, this is I think obvious, but let's draw plot the other case, this case. Is gonna move to the step function, but let's also plot this case where I have actually a decreasing or decaying exponential, right? I mean, it's a, this is an, I mean, these are, and maybe it's 0 on this side, okay? Or however you define it. To make it 0 on this side, actually, we need a step function. We need a step function multiplying the signal, okay, to 0 it on this side. Multiply the signal to start or to make it 0 on the negative side. This is good because we typically work with finite signals or signals that start at some time point. So that helps us to define such signals. So first let's define x of n is u of n. Okay, so this was one example. This is now another example. This guy, now step function or step sequence in the discrete time case. When I say step function, it's going to be more like the continuous case. So it is zeros for all n negative and starts as 1 at 0, 1. This is Heaviside function in mathematics, also step function, but in discrete time. Okay, it continues in this way, step sequence. Units, here it's, if it's 1, it's called unit step sequence. Okay, so let's write it. Unit step sequence. We should know these, okay? This is an exponential, we should know exponential sequence. Signal or sequence, discrete time signal, unit step sequence, let's say. And here I should say recall, or we will see maybe this, but I think it's good to know at this point, recall the u of t, sorry, t. I don't know if we've seen this, but maybe we have not. This is the continuous version of it, okay? So there is a jump here, you see, it's all zeros and all of a sudden jumps to 1, and then it's all ones. These are really that multiply signals that multiply our signals to indicate something starting, a starting event. For instance, in a circuit, maybe you've seen this in your circuits courses, a switch is turned on or closed, then a signal starts to flow through the circuit. That's how you model it. You say, hey, at this time point, there is a u of t. But of course, it could be shifted. If, for instance, it's u of t minus t0, it's going to be shifted to that point, right? T0, let's say, it's going to be 0 until that point. And if the switch is turned on at t0, it's going to be really only start to be 0 at that point. Same thing, similar thing with our step sequence. For instance, u of n minus 3. Okay, just a sec. Or u of, let's say, n minus 3. It should really start at 3. So it's going to be 0, 1, 2. It's going to be really 1 here. And it's going to continue like this, okay? And so 1 at those points. Okay. Then from here, we can, for instance, look at things like, let's say, u of n minus u of n minus 1. What is this sequence? So you can just go and plot this sequence, guys. You can say, hey, u of n was really this signal, this sequence where I have really all ones. It's a step function or heaviside in discrete world. It's an infinite sequence, actually, you see, of these numbers of ones on the positive side of my axis, time axis. Now I have u of, this was u of n. Okay, let's just see what this signal is. So then I would say, hey, let's get u of n minus 1. Shift this signal, right? Shift it by 1. Now it's 0. I mean, it was also 0 here. It's going to be 0, 0, 0, but now starts to be 1 at 1. 1, 2, 3, 4. Guys, just now take the difference. Now this difference signal is here. What is it? It's really what is remaining at the n equals 0 index, right? And it's all zeros everywhere because they have the same amplitude. Okay, so this is called, we give this a special name. This is a unit impulse sequence, guys. So this is really, okay, sorry. This is my 3D vision course all of a sudden coming up. Okay, so this is delta n. We call this is defined to be delta n. It is unit impulse sequence. Okay. This is also an important signal that just samples from signals. We have its actually continuous time version, which is a little bit more difficult to understand, but it's here easy to understand. Delta of n, I can have a shifted version. For instance, what is delta of n minus 3? It's gonna be, this was delta n. I think you guys get the point. Just go there. Maybe let's make it 2. If it's 2, I have to really have amplitude 2. I mean, it's not in scale, but, and it's 0 everywhere, but it's non-zero at the index n equals 3 with amplitude 2. That's it. Okay? 4, 5, minus 1, minus 2. It's all zeros everywhere. Okay? So delta n is really 1 for n equals 0, 0 for all other n. And not equal to 0, for instance, and the same thing for the others, the shifted versions. So for instance, also we can create other step functions like, or pulse, or actually we can create a square pulse. For instance, what is u of n minus u of n minus 4? I think you guys can now imagine this. This is gonna be 1 at 0, 1 at 1, 2, 3, but it's going to start to be 0 at other indexes. This is now like a square pulse, right? Because you see, it's really something like this, right? This guy. This is to limit a signal to some certain time range. We have its continuous time version. So the continuous time version, let me say, for instance, u of t minus u of t minus 4 is really, is a square pulse wave. So let's just draw it here, t 0 to 4, 1. So it's really, you see, a square pulse. It's called square pulse wave, used also by in EE physics a lot. So, but you see the equivalence in a way, right? So I think this is enough introduction for type of sequences. We've defined some general ones. For the delta, we will look at its continuous time version, which is a generalized function, which is not a regular function because it's an infinite. I mean, there is an instantaneous infinite jump at, for instance, t equals 0. That delta of t is a little bit trickier to define. We will look at it in continuous time. So, okay, now important thing is sinusoidal, the discrete time sequences. Sinusoidal discrete time. This is what we wanted to study today. Sequences. So discrete time. First, maybe let me write the continuous time version. Remember this. I think we should really do this conversion. Recall, this is a recall. Recall continuous time sinusoid. Okay. So let's write x of t, a, okay, let's write with phase, the general version, omega t plus phi, okay? Now go to, actually we go to the discrete time mathematically through something called sampling. Remember x of t, there is a system here which is analog to digital converter, or we sometimes call it discrete, continuous to discrete converter equivalently. And the operation of this, we haven't yet studied systems. We will be coming to that after we study this discrete time Fourier series, but it's soon. But I mean, you can imagine, I was telling you before, this is like an algorithm, takes an input, produces an output. Here, this result here is, or the mathematical operation is, x of nts. Let's see. So this is really x of nts, which is really x of t sampled at t. You see, we've just done this. This is sample the signal, like here, I think. Every other ts samples, like the one we're showing at the top. So I'm writing this operation really mathematically here, okay? Of nts. So now insert this for the discrete time. To obtain the discrete time, insert this mathematical operation. Okay, this is the sampling, uniform sampling operation. Uniform sampling operation, or this is, let's call a system. Input is x of t, you see this is the output. Okay, because this can easily be converted to x of n. You see, take the samples, change the index to an integer index, right? And becomes our discrete time signal, actually. That's it. So discrete time sinusoid now, let's just do the math here on x of t. So just go there and say, I will sample it every ts seconds here. Therefore, with this system, you have to define a parameter, guys. You have to define this discrete converter with ts sampling rate, or its sampling periods, of course, rate. The frequency will be 1 over ts. Okay, this is the parameter of this system. I mean, that means you have to specify that parameter, okay? I mean, if you talk about a continuous to discrete converter, you have to know how frequently you're taking your samples, and that would be the sampling frequency, actually. So from here, of course, we will have fs equals to 1 over ts, our sampling frequency. This is important. Both of them are important, actually. And I can have the angular frequency version, remember. The omega s will be 2 pi fs. But okay, we will define it here. So now apply this operation, I mean, to the output to get the output. Actually, remember, this will become our x of n. So now let's do this math. This is equal to a cosine omega times nts. So let me bring ts first. I mean, this was actually, now this is t. T is n times ts, or ts times n, right? This is exactly what we did here. Sorry, let's do it. Okay, this is it. So t is n times ts. This is the relation to go from t to n. Take every ts samples. Okay, so now I continue here. Plus phi is already there. Okay, so you see now we will define a new digital frequency, or which is a normalized frequency. This is important. Please pay attention. We define this to be omega ts, which is equal to omega over fs. You see, this is normalized frequency. Normalized, these are our continuous frequency value, this time, or the frequency that is valid in our continuous time signal. by the sampling frequency, we get a normalized frequency. I mean, not that guy is normalized. The whole thing is normalized, okay? Normalized frequency. This is important, omega hat. Okay? So now that means for sampled signals, X of n, this guy, X of n, output is this guy, right? Seconds, or X in square brackets n. The frequency we're talking about is actually omega normalized by the sampling frequency. So we should really do that conversion. That's important. Okay? So one thing also important here, I can note here, guys, is when we said there is a sampling frequency, there is a sampling theorem. We will come to this later in more detail. Let me write this also here for your notes. We'll study sampling theorem later. Here I'll just state it in Fourier domain, Fourier transform domain, okay? Now I'll state it in time domain. Very roughly, we should pick, for proper sampling, I will show you why we should pick a sampling frequency which is double the frequency, actually maximum frequency or existing. Of course, for a sinusoid, it's the F0 or whatever frequency we have. It should be at least twice of that frequency. We should pick a sampling frequency. Okay, this is to sample a continuous time signal, of course. Time signal. At least in this case, I mean, if it was omega, let's make this omega 0 maybe just to relate in this case, or maybe let's not, to sample a continuous time signal, let's say, I mean, this is just an example, sine omega 0 t, okay? At least two times f0, okay? So fs should be greater than 2 times f0. This is a very much celebrated result, sampling theorem, Nyquist-Shannon sampling theorem. Because if you do this, then you can reconstruct signal, the continuous time signal, through a discrete analog digital analog converter or discrete to continuous converter. We will study these in more detail after the Fourier transform, because these are really like applications of the Fourier. Okay, so now let's continue. We said now I have sampled my signal. Okay, here. Okay, now you see from here, actually, let me write it for your note. I end up with this sampled signal. You see, this is the sampled sinusoid, discrete time. Let me rewrite it. X of n cosine. Let's just just ignore the face for this moment, because I want to say this. Let's say, I mean, I know this is a fundamental period and it is periodic. Okay, let's say it is a fundamental period. This time it's gonna be in integers. Okay, n. I mean, this is really like this. I mean, if it's a periodic signal, so let's say it's a periodic signal like this. I'm just making it up, not this cosine signal. Okay, it's just a side note. For instance, I could really be repeating this guy. I'm gonna ask you what is the fundamental period. That's why I'm drawing this now. Let's say it's repeating itself. Say this is an example. Okay. Oh, okay. All right, this guy comes here. Okay, so let me just maybe give some numbers here so that you guys can, maybe there is always one in between. Okay, so what is the fundamental period in this for this signal? Okay, my question to you is, let's see. Do you guys have an idea? I mean, just fundamental periods. This is an EG. I'm just giving an extra. This is not a sinusoid currently, but example, I'm asking you what is fundamental period of this signal? Because I mean, it can be also integers, right? Yes, 4. Thank you, guys. Exactly, 4. 4. N is 4, right? So because the signal, I mean, guys, just look at this. Signal is repeating itself in which intervals, right? So you can just pick this, the 2 peaks between the 2 peaks. It's 4. N is 4, okay? You can see it, and it repeats itself in every 4 samples. Perfect. I think now it's clear probably. What is a fundamental period in the discrete time? It's the same. Now it's just number of samples that the signal repeats itself. There are cycles of the signal. So let's say now this is still a discrete time sinusoid, a specific signal, right? I mean a certain signal class. So now let's say I know at least cosine R, let's see, cosine omega 0 hat. This is, you see, normalized frequency. Let's add multiples of 2 pi on top of omega 0 hat. This is, I know cosine, right? Is here, this guy is periodic with 2 pi, but let's show it's gonna be, it will repeat itself with some multiples of this time. So I know x of n is equal to x of n plus n. So maybe let's write it here. Then I could say x of n is really x of n plus n. Now also write x of n little n plus capital N here, which is cosine omega 0 hat n plus n. Okay? Now equate these two. I can come up with, we will come up with something. So from here, I can see that omega 0 hat times n is equal to omega 0 hat, right? Omega 0 hat n. No, actually, I need 2 pi k n. Okay, this is really 2 pi k n. At n is 2 pi k. I need to stay with 2 pi k, so I'm trying to see, I'm right now, right? Omega 0 hat n is omega, am I correct here, guys? This is it. This, yeah, because k times n, that's another integer. That's why, okay, let's just bundle them together onto a k. I have it in k in my notes, which is correct, which is fine. K dot n doesn't matter here. It's another integer, okay? Another index. So here, this is what I'm trying to get. So from here, guys, you can see that this normalized frequency of the sinusoid divided by 2 pi should be ratio of 2 integers. So that's a rational number to have a periodic signal. So this is to have a periodic discrete time sinusoid, by the way, periodic discrete time sinusoid. Because I may sample the signal so that it's not becoming periodic anymore. That's an interesting fact about discrete time sinusoids, okay? So to have a periodic discrete time sinusoid, I can equate these two expressions I'm showing at the top, and then I come up with this ratio. It's a rational number, meaning both numerator and denominator integers. If this is a rational number, then I know I have a discrete time sinusoid. Okay, here is a little bit, I mean, it may look a little bit confusing here. I have so many new things defined because, for instance, from here, I can say I know omega 0 hat over 2 pi is f0 hat, right? I can define now the normalized regular frequency, which should be ratio of 2 integers. I also know from the earlier definition, remember, I have a definition here, this guy. omega 0 hat times Ts is omega, sorry, omega 0 times Ts is this guy, sorry, omega 0 hat is omega 0 times Ts, yes. So this guy is 2 pi f0 hat, which is 2 pi, let's go to the f0s, f0 Ts. From here, f0 hat is f0 times Ts, okay? Now bring it, this is another definition. You see, actually, this is really equal to f0 over fs, normalized. Just remember, we are normalizing frequency by sampling frequency, regular frequency in the continuous time by sampling frequency. Now bring this into this formula. Now I have, there are so many insertions. You have to go over these also, please, after the class on your own. I'm rewriting things. It's so simple, actually. Ratios of things here and there. Now I'm trying to come up with this. That's the thing. From here and the end, we came up with, guys, this guy. F0 Ts is that. So F0 over Fs, because this is 1 over Fs, is K over N. Okay? So you can see that, I mean, the fundamental, the frequency in the signal times the fundamental period, and it should be, these should be actually, and the sampling frequency, these should be multiples, you see, integer multiples of each other. The frequency in the sinusoid and the sampling frequency should be multiples of each other so that I end up with a periodic sinusoid. I think that makes sense, right? That's fair. Okay, so these are some things to maybe remember when going from this continuous time to discrete time, sinusoid. It may look a little bit confusing, but actually it's fine. I can also write this in terms of the periods, fundamental period and the sampling period. Write it also, can write it easily also as, we can just say K times T0 and N times Ts. I mean, it's here actually, because of the inverse relation between sampling period and sampling frequency and the frequency and the periods, T0 and F0, of course. I know this is looking too many parameters, but it's really, there is a sampling period, sampling frequency, which are T0 and, sorry, sampling. So it's TS and WS or FS, 3 of them. And then we have the sinusoids on frequency F0 and T0, okay? That will be the fundamental frequency, of course. Because I needed to define these, we want to move to a Fourier series representation. Okay, so let me see if I have, yes, I have defined, we have made some important definitions. By the way, I should also note this, guys, for discrete time sinusoids, this is a note, discrete time sinusoids. They are only unique up in some range. We've just shown this actually. They are the same if you shift them by 2 pi k multiples. So let's write this. If you shift this frequency, if you shift the frequency, okay, by 2 pi multiples, let's say, by integer multiples of 2 pi, okay, I get the same sinusoid. Let's write this. You end up with the same sinusoid. You end up, this is fact about discrete time sinusoids, okay? You end up with the sinusoid. So for instance, if I have, let's say, an omega 1 hat normalized frequency plus some integer times 2 pi, multiples of 2 pi, just do the math here. So go to sine omega hat, 2n, this is a discrete time sinusoid. Insert its formula here, or its equivalent form here. If you do your math, this is easy to show. You guys know this by the trigonometric identity, right? I think maybe just as a hint, I can write this for your notes, omega hat plus m2 pi. And I forgot the n here, guys. This is important. Of course, there is a time variable here, which is n, right? Okay. And you guys should just open this up or expand this. Time cosine m and 2 pi. I think we derived this by Euler formula before, so it should be fine. Okay. So let's see, plus cosine omega 1 n times sine m and 2 pi. Because these are, this is 0, this is 1, you end up with what you want. Okay. So therefore, discrete time sinusoids, guys, this is important, are only unique over, this is important, unique over, it could be any 2 pi interval, but let's say we just take it. Okay? Could be, I could say, could be any 2 pi interval. So they are only unique in a 2 pi interval. This is different from, now contrast this to continuous time frequency or the continuous frequency omega. So this is the difference between omega. This did not have, omega did not have this property. Omega does not have this property or constraint. Okay? Let's say property. Okay? So in this way, actually, let me also note this. This is note 1. This was important. This is good. Note 2, then what are the low and high frequencies? Remember, with continuous time, we were like, hey, small frequencies closer to 0, of course, right? I mean, the lower frequencies and very high frequencies, they can go to really, really high, thousands, millions, rate of oscillation. But for discrete time, they should really be in here, meaning those frequencies around 0, and these are also periodic with 2 pi, remember. So the frequencies close to 0 or multiples of 2 pi plus minus are low, and those frequencies that are around pi and its 2 pi multiples are high frequencies, actually. So we should say rate of oscillations of a discrete time sinusoid, okay, increases from, let's say it was omega 0 at 0 to pi, okay, and decreases, then decreases, let's maybe write this here, then decreases as omega 0 hat goes from pi to, let's say, pi to 2 pi. This is important. Okay? So this would mean low frequencies. This is important. Low frequencies, because you will be working with discrete Fourier transform, discrete Fourier series. It's important to know that's how you will display things. When you see things, visualize, for instance, and manipulate, closer to 0 frequencies are your low frequencies. So low frequencies of discrete time sinusoids are, let's say, are in vicinity of omega 0 hat is 0 plus, like I was saying, 2k pi. Okay? And high frequencies of discrete time in vicinity of, let's say now pi, I should say plus minus, by the way. And here it should be really pi plus minus 2 pi k, 2k pi, or k could be negative or positive also. 2k pi, k an integer. This is important. Okay? So let me, I was Trying to see if I have some, first of all, let's show some sampling. I think this was marked. I don't know if I can, I can clear these. Okay, but it can stay, let's see. So my point here is to show you, guys, two sinusoids, continuous time sinusoids at the top. Yeah. Okay, Mehmet is asking a question. Mehmet, let's go. I'm sorry, where is my, what is it you asking? I didn't write A, anyone, zero. This is zero, yeah. It's around zero frequency, okay? So low frequencies are around zero, okay? Zero frequency, around zero, and high frequencies are around pi radians, of course, right? Pi radian frequency, okay? Mehmet, fine. All right, so let's look at this picture and then give a break. It's already more than 50 minutes. So I think we were looking at this. I was trying to show you here in this slide. There are two sinusoids. One is blue, guys. Look at this blue sinusoid here. You see this blue curve, right? I just shown. And there is a green sinusoid. One of them, these are continuous time, nicely displayed. You see one of them is a low frequency, the blue one. You can find its frequency by really taking, actually maybe just do the frequency finding by really finding peak between the distance between two peaks, right? It would be really this guy. How much? It's 10 seconds. So T0 of the blue curve is 10 seconds, blue sinusoid, right? The fundamental period. It's repeating itself every 10 seconds, you see. So its frequency is 0.1 hertz, okay? So its frequency is really, so F0 is 0.1 hertz. Now look at the green one. Let's just also pull its frequency. It would be, let me see, can I really calculate it exactly? What is the distance between two peaks? The green one, can you guys pick two peaks? Maybe it could be almost 5 maybe, but maybe not. Trying to see if I can pick something.
10/12.
10 over, what is it? What did you say? I'm trying to pick two peaks, but I was not successful, but let me see. You guys can try to check with me too. Yeah, we have the formula here, right? Thank you. I didn't see, guys, look. We can find it. I mean, I was trying to search it from the figure, but it's not that fine enough. Now let's calculate it from the mathematical formula. Thank you. Yes, you guys check this. Thanks, Fuat. But here, actually, guys, blue curve, this is really then the sinusoid, right? It was cosine. Okay, x of t is cosine, blue curve was blue one, pi over 5t. I mean, you can see this is really it because F0 is 0.1 hertz, then W0 was 2 pi 0.1, right? Because it's 2 pi F0, 2 pi times 0.1, which is really pi over 5. Now the green one, X green is cosine. It's written here. I'm going to really just copy it. 11 pi over 5 t. So from here, I know my omega 0 is 11 over 5 pi. And from here, it's 11 over 10. F0 is 11 over 10. Okay. It's here. I already wrote it. Anyways, guys, let's clean and rewrite it. Okay. The blue one was pi over 5 radians per second. It's written. The green one is 11 over pi radians per second. From here, f0 is, we said, right? F0 would be just divided by 2 pi, then it would be really 11 by 10 hertz, right? From there, you can find the fundamental period, which is T0 is 10 over 11. I think you guys were very close. Thank you. 10 over 11 seconds. Almost one, right? A little bit less than one. Almost one period intervals. It's repeating. The green one is much higher frequency, you see. So now, so let's see, okay. So we will now do a sampling here, okay. So let's see here, okay, from the graph actually, we see that the sampling from here, the first one is a sampling, the middle graph is a sampling of the blue curve, okay. So you see it's written here, discrete time sinusoid pi over 5n, it's written here. Now it's actually sampled with Ts equals 1 seconds. Okay, you can do the math. Go from cosine pi over 5t, okay, to, please do these at home also, t, to now do this omega Ts, which is 1 second. So that's why really omega Ts use, this is really pi over 5n. It converts me to this sinusoid, okay? So now this is really taking samples every 1 second, okay? You see, I got a sinusoid, which is nice. And I have to check if it's a periodic one. It is because, remember, we wrote this, right? N times Ts, it's already here, which is nice. I don't need to memorize. It's K times T0, N times Ts is K times T0. If this is a rational number, Ts over F0, remember, or Fs over Fs, F0, if this is a rational number, then I have a periodic discrete time sinusoid sign, which is correct. Here it is, because it was, Ts was 1 second, Ts, T0 is 10 seconds. It's 1 over 10, okay? That's a rational number. Then let's see, and the fundamental periods of course here is just pick 2 peaks here to here, right? It's really, and fundamental period is 10 samples, which is good. But now see the second green one, sampling of the green curve, it's at the bottom, sampled again by 1 second. This is now, you see, cosine 11 pi over 5n signal. It's written here already, I rewrote. It's the same signal. What I'm trying to show, guys, is non-uniqueness of the discrete time sinusoid. Why? Because we said actually there is this relation of the frequencies that are related by 2 pi multiples. This blue curve was, it was pi over 5, right? Radians. Add 2 pi to that. So it was pi over 5 plus 2 pi. It's 11 pi over 5. So you see the relation. They are in discrete time. They are the same sinusoids. You see, these two are the same sinusoids. Exactly, we obtained the same signal. That's why we typically try to pick the, actually, or state in our discrete time sinusoids, stay in the lowest frequency possible, because I know on top of 11 pi, I can add 1 more 2 pi, and I know that I have 21 pi over 5, which is also the same sinusoid, okay? Salih, thanks. John, TS sampling, how do we determine the sampling period? It's arbitrary, it's up to you. It's your system parameter. That's why I mentioned it and emphasized it. TS, we could pick another TS and we will end up with actually a different discrete time sinusoid. Good point. So let me see if I have other examples. Let me see. Okay, this is just from the slides, guys. We've just learned actually this part, continuous to discrete time. Later we'll talk about systems here, and we will, for instance, manipulate our signals in discrete time, and then by a discrete to continuous converter, we will come back to the continuous time. Continuous time, here I have my discrete time signal x of n with its own normalized frequency omega hat, and the overall analog system would be x of t directly multiplying to yt. This is a continuous time system, but this is a discrete time system. We will study both of them, okay? But now it's important for you to know the difference between, just pay attention, omega hat and omega, how to go between the two. This normalized frequency is important. This is our regular frequency, or f and f hat, it's the same thing, of course, the same 2 pi multiple. Normalized frequency, this is used for discrete time signals, okay? Because we have to normalize this W by the sampling frequency to go when we work in the discrete time world, okay? Yes, it's not possible to know. Fuat, thanks, very good question. We won't, it's not possible to know when you go back, very good question. So typically, or the rule of thumb is to go to the lowest frequency possible. So in this case, it would be, you won't be able to know actually if you don't sample more finely. Here in this case, the continuous time signal we are returning to would be the blue one, okay? If you sample, very good question, with this sampling rate. If you sample much finely, right? For instance, instead of 1 second, go to just 0.01 seconds, lots of samples, then you will differentiate between the two. We will study this more in detail in the Fourier domain. Here, that's called aliasing also. In the Fourier domain, we call it aliasing. We can also see it in, we can see the effect in, of course, coming back to a different signal. If we started with the green signal, we sampled it, we would be coming back to, for instance, the, let's say, the blue signal. Okay, good question. So now let's give a break, okay, and then come back and continue with this interesting discrete time signal topic. I know it may sound a little bit more difficult, which is you have to know how to go between these things. Okay, we were here, or where were we? I'm trying to see. But I think it's gonna become clear if you go over the notes, okay? All right, so let's come back after the break. All right, so now let's define Fourier series representation for these discrete time sinusoids, okay? We've studied in the first hour how to sample go from a continuous time signal to a discrete time signal. We defined this normalized frequency, sampling frequency and sampling periods, and normalized frequency of a discrete time signal was actually division or normalization of the frequencies by the sampling frequency, right? All right. Now I'm going to define, okay, it's here, a Fourier representation for these signals, okay? Fourier series representation. For discrete time signals. Okay, so now it's gonna look very similar, but with basis functions are of course discrete time sequences now. But let's write the synthesis part first. Synthesis equation for a periodic signal. But of course, it's a discrete time signal. X of n with periods, let's say, this n, and it's an integer, right? N is an integer this time, that's why. And an integer, of course. Now x of n is equal to, let's say k, okay, k 0 to n minus 1. You see it's finite number of them this time. Ak, and I have my basis function e to the j 2 pi over capital N k n, okay? So I think this should look somewhat familiar to you. These are my Fourier series coefficients, okay? And I have the basis function phi k, let's call this phi k, which is equal to e to the j. You see it's a family of basis functions indexed by k. Remember, I'll write the continuous version also, so you guys can make the connection, okay? This is my basis, or this is Fourier series basis, or Fourier basis function. I mean, discrete time, of course, okay? Maybe just to recall here, let me do a recall here. Recall Fourier series for continuous time signals. The analysis was, recall, x of t, sum ak. Here, k was, guys, it's for continuous time signals, infinitely many, okay? But we will see that these ak in the discrete time are periodic. That's why we just need to look at it in one period. N of them, capital N of them. Ak, and the basis function was e to the j omega 0 t, k omega 0 t, or maybe I could write omega 0 is really 2 pi f0 t. Remember, this was the basis function, right? Basis. The continuous time case, Fourier basis, of course. But now also pay attention to these infinite sums. Here it's a finite one. So Fourier series coefficients of a discrete time signal. Periodic signal, of course. Time periodic. Here, periodic is important. If not periodic, we will write a DFT later, okay? So this is period n. We said x of n has period capital N. So remember, here it's really like omega 0 hat is 2 pi over n, okay? So 1 over n is really like somewhat, f0 hat is like 1 over n. So you see from this basis equation, I'm saying this. So let's write this basis nicer. I think it doesn't nice to me somehow. Phi k e to the j 2 pi over n k. Okay, n. Yes, I think that's good. K, you see, is the index here. So basis function, these basis functions are complex sinusoids now, remember. So these are really, really complex discrete time sinusoids. And remember Euler's formula. With Euler's formula, I can really write it as a cosine plus sine, which is the same thing. So maybe we could write this also with a, let's maybe write it here as a note for your notes. For a complex sinusoidal sequence, let's say, note, complex sinusoidal, okay. X of n is a e to the j omega 0 hat n. Let's just use the Euler cosine omega 0 hat n plus j a. Let me just write it more compactly. Okay, this is then just to note. I mean, this is a complex sinusoidal discrete time, of course. So now these Fourier bases, these discrete time Fourier bases, the other one also live on the unit circle, but let's say Fourier bases live on the unit circle. in the complex plane. Circle or on the complex plane, let's say on the complex plane. So I'm gonna draw a complex plane here. Guys, let's make it nicer. Maybe here and here, real, imaginary. Let's say this is 1, 3 of them. Okay, so I have to go a little bit more here. It should be really, this is imaginary axis, okay? This is 1. Actually, they will live on the unit circle. So just a sec, I need to go to here, right? -1. Just this is like the envelope, so it should be here then. So now I want to look at these Fourier bases. For instance, phi 0. It's really 1, right? It is this guy. It's equal to 1. This guy is phi 0. Phi 1, k equals 1, just e to the j, 2 pi over n. It's somewhere here. Phi 2 is, let's make it, okay, I actually draw it for a specific case. Let's say, e.g., say n is 12, okay? So let's insert it actually here. So phi 1 is really e to the j 2 pi over 12. So pi over 6, which is 30 degrees actually. So this is somewhere here, which is correct. Now 2 pi over 3, 60 degrees, phi 2. You guys can see this is phi 2 e to the j 2 pi over 3 now, right? And then phi 3 would be really e to the j pi over 2, which is on the imaginary axis. Okay, this is phi 3. Phi 4 is somewhere here. By the way, I have to do these guys also. You guys will see. Okay, this is phi 4, phi 5. You can do the math. I mean, just insert the mathematics here from our basis function definition with a specific fundamental period, capital N. Okay, I'm just drawing them here. We will start having complex conjugates here. Phi 6 is -1, by the way. Just do the math. For instance, phi 6 e to the j 2 pi over 12 times 6. So it's really e to the j pi, which is -1, right? Phi 6. Guys, it's really repeating. It will start go to the complex conjugate. So phi 9, phi 10. You can just calculate maybe one of them, phi 11. And you see phi 12 is back to, I mean, these are, by the way, okay. These should be also solid lines. And actually phi 12 will be really equal to phi 0. It's come back to the same location. Okay, this is important. And one other observation from here is some of these, because they are complex conjugates and you see the symmetries on this unit circle, some of, let's say, the sum of the basis function, sum of the basis on the unit circle, k0 to n minus 1 is actually n for, so let me write the basis here, e to the j 2 pi over n k n, k, okay, actually, k of n, phi kn, phi k. Maybe actually I should have phi to the k is this guy, but I need of n actually, guys. So this should be really to the power n. Here I picked, I have to really, yeah, I have to really have a, okay, let's see. Phi k of n this was phi k, and I want to say here, guys, this is equal to n for k equals, I went to the sum of the bases over, this is a time integral, time sum. The other thing is also valid, but this is a time sum. You can also show it n0 to n minus 1 is equal to capital N k for 0. And I need, I think, plus minus n plus minus 2n. You can also see that sum of the bases. These, I mean, what I'm trying to show is these bases show the property of zero sum. Remember, we've seen it for discrete time Fourier, continuous time Fourier series basis, zero integral property, and also orthogonality property. These bases also show that. Okay, so I can say the others, all other unit vectors, UK, VK sum to 0. So this is 0 to n minus 1, VKN is 0 when k is not actually, is not equal to these multiples of this guy. You see, when I don't have this one term, everybody else cancels each other, right? Am I doing this correct? It's equal to 1. Yeah, all on unit vectors sum to 0, VKN. So let me see. I'm trying to show you maybe some examples of this AK. Okay, I want to mention AK property. So let's rewrite this AK. How do I write AK? We didn't write the analysis integral actually. I should also write the, okay. What about, this was the synthesis equation. So let's see, analysis equation for the same thing. We didn't derive it. So we start from, remember, let's start from synthesis. Okay. X of n, we said, is really AK, right? AK, e to the j, 2 pi over n, k, n. I mean, basis functions, k0 to n minus 1. Now, remember, last time what we did was multiplied both sides by another basis function with another index. Multiply by, let's say, and the complex conjugate, e to the minus j, 2 pi over n, let's say mn. You see here it's k index, here it's an m index. Multiply both sides by this guy, and it's the same equation. This is exactly what we did in the continuous time. Let's do it here. It's really telling us how to obtain the analysis equation. Obtain analysis equation. X of n e to the minus j 2 pi over n mn is k0 to n minus 1 ak e to the j 2 pi over n k minus m, right? And yes, I can do the exponent sum or definitely directly. So here, this was what I was trying to say, guys. Now sum it up. Yes, first let's sum it up in time, 0 to, in one period. Let's sum it up in one period. This is what we want, 0 to n minus 1. But on the now left-hand side, I have actually what I want, 2 pi n mn. Here, AK sum goes out. I can really exchange the order. And I used the property of the orthogonality property of these basis functions, e to the j 2 pi n k minus m n, and I know this sum is 0 for k is not equal to m. Zero sum, this is zero sum property. We've seen over here actually everybody, you know, had their symmetrics, right? The symmetric versions. When I have actually look at this sum, k is not equal. When k is equal to m, zero sum property actually. So let's see. When k is equal to m, what happens? For k is equal to m, I have my sum n 0 to n minus 1. 1 actually, yeah, e to the j0. This is sum n times, so it's really n. Yeah, it's equal to n for k equals m, e to the j0, or multiples of 2 pi actually. It ends up on the always the real axis, right? So now that would mean this is really valid only for k is equal to m, okay? So I really have ak, the synthesis or analysis equation, meaning how to obtain ak given an xn signal is this 1 over n, okay? This is what we have, n 0 to n minus 1, sum it up in one period, x of n, we said ak, so I'll just switch back to k, not m, e to the minus j, right? 2 pi over n km. Exactly like what we did in the Fourier, the continuous time Fourier case, Fourier series case. Okay, so this is how to find, how to calculate Fourier series coefficients, given signal x of n, and of course we should define its fundamental period. Okay? Now there is a specific property for these AKs in discrete time. In continuous time, remember, these AKs did not have any periodicity property, but for discrete time signals, their discrete time Fourier series, this is discrete time Fourier series, that is, has a special property. Let's look at that. Just add n to this k. They will be periodic with the fundamental period, actually, k plus n, because of the, by construction, just rewrite this analysis integral, 1 over n, right? It will be n 0 to n minus 1, x of n, e to the, what was it, minus j 2 pi over n, k plus n, n. Okay, I'm just rewriting it with ak plus n. So now what is this guy? Let's look at it together. 2 pi over n kn, the Fourier basis, times e to the minus j 2 pi over n times n, n. These go, e to the minus j 2 pi n, that is equal to 1, right? In the discrete time case. Remember, this is not 1. 2 pi t, sorry. Is this 1? No, because this is continuous. Whatever t is, I may end up on somewhere on the real or imaginary axis, I mean the complex plane somewhere, right? I'm trying to see, for instance, t is 0.01, I end up in some place here, right? Arbitrary, but for the e to the j, 2 pi, and things are different, but that is always because n is an integer. Remember, this guy is always ending up as on the real, actually. This always ends up on real line at 1. Okay? So that's why it's 1. And you see, actually, we have this guy equal to exactly the same expression before, e to the minus j 2 pi over capital N k n. This is really equal to ak. So we should say This is telling us Fourier series coefficients, or let's say this here, Fourier series coefficients for a periodic signal, for a discrete time, periodic signal is also periodic with the same period, okay, with the same period actually, period n. This is important. Okay, so I mean, this is important because it's really nice. It gives us some finiteness, meaning I just need to calculate this AK for n of them, capital N of them, which is really good, guys. Okay, this is what we have. So we've just shown the analysis equation and synthesis equation for discrete time signals. Recall, this will come later, but just to note here, because you are using this in your homeworks already, for a non-periodic signal or any signal actually, discrete time, non-periodic, so any discrete time signal, okay, important non-periodic signal, I think because you guys already started to use it, I have the similar x of n is this time, guys, if it's non-periodic, it's going to lead my k to run from minus infinity to infinity. So periodicity gives us some compactness, you see. These are the actually discrete Fourier transform, discrete time Fourier transform coefficients now, ak e to the j 2 pi k over n. And I'm not doing it formally, just for your notes because you are using it. Okay, so n is the time variable, remember? We call this k the frequency variable. Okay, and just note the infinity. So this ak will be when we say they are equal to 1 over n. So we will define, you see it was 1 over n here, right? So rewrite everything maybe, synthesis. Let's write it here. Synthesis was x of n is sum ak, and these were really finite, e to the j 2 pi over n kn, and then analysis was the general again, just to repeat, 1 over n k 0 to n minus 1 x of n. Remember, it's minus now, just be careful, 2 pi over n kn. Okay, synthesis and this discrete time Fourier series, but this is here, guys, note, summary, this is summarized for a periodic signal, for a periodic x of n. Okay, periodic is important here. With n period here, fundamental period. This was the summary here, the analysis and synthesis equations. So you see this 1 over n could go ak. Okay, ak was 1 over n already. Okay, we will, this is actually, you see, relating to the discrete time Fourier coefficients, ak 1 over n xk. So let's see. So we called now, just this is an extension, but we'll do this later. We called this guy, the k is really our frequency variable here, the discrete time version of, or discrete version. And our DFT, the discrete Fourier transform that you guys use, then is really, this is, you see, the frequency domain representation of x of n, like the ak. So here ak is frequency domain representation, right? Those coefficients, Fourier series coefficients of x of n. What you're doing generally is we have this DFT, discrete Fourier transform, frequency domain representation of x of n, which is really equal to, now it could be an infinite extent signal. Typically, of course, in our finite world, we truncate them. And this is really normally what we do is really this is n minus m to m, of course, right? We take a finite in practice. We don't do minus infinity to infinity, but the math is like valid for infinity to infinity, e to the minus j 2 pi over nk. This is, you see, and dot n, the basis function. We call this, due to this n point DFT. I think you started taking this, so remember, I think probably you guys are using, or maybe it's very soon, fast Fourier transform f of t, which does actually goes from xn to xk. So it's really time domain to frequency domain. And inverse FFT, inverse fast Fourier transform. These are some fast computations to, for instance, take this endpoint FFT as multiples of 2 and things like that. But it's not, I mean, we're studying the theory here currently, not the practice. You guys will do these in your homeworks. This is, we said already, this is endpoint DFT. So I wanted to say, guys, actually, the inverse FFT takes my Fourier series, Fourier transform coefficients. This is capital X, by the way, right? And the frequency domain variable K, and goes to little x of n, okay, to time. So this is an extension, and just to note here, you are using this in your homeworks, let's say, in your homework assignments, right? In your homeworks. Just to note, but you see, it's really just an extension to non-periodic signals, okay? But here we just have to define an n, a capital N. It's non-periodic, there is no fundamental period, but we have to limit, it's a minus infinity to infinity, we have to limit this integral to some range, and actually that's gonna be typically relating, these limits of the sum relates to also capital N. But this is a little bit digression currently. This is for your homeworks. For the mathematics, you are currently yet not responsible from this slide, okay? But you will be using it practically. So now let's continue. And what we did is we really defined the Fourier series coefficients, how to calculate it, given a discrete time signal, or given the Fourier series coefficients and the fundamental periods, or fundamental frequency, 1 over n, right, in a way. And we have multiples of it, the harmonically related, actually. When I have k, I know how to obtain the signal. Any questions? Okay, so let's see, guys. Let's check some more examples. Or let's do an example to calculate AK example. I think this was, I'm going to show it later, but from the slides, an example from the slides. So this is a sinusoid. Let's start with even the continuous time. Let's just see, sample it. Cosine 2 pi 100t. Remember, this is a 100 Hertz signal, right? So from here, you guys can directly say, hey, it's 200 pi radian per second. F0 is 100 Hertz. I have T0, which is 0.01 seconds. And from the sampling theorem, I know I should pick my Fs greater than 2 times F0. So it should be, this is from sampling theorem, note, Fs should be greater than 0.2, 200 Hertz. I was going to this period already, 200 Hertz. Actually, then Ts should be less than, I could say, 5 milliseconds. Okay, I think I can note, this is slides, DSP first slides. We will look at it, but just for your notes. Slides 09. This is for an example from there, okay? We will look at the plots now. Let's do the math on the tablet and then look at the plots there. Now, first sample x of t at a given, for instance, 0.5. I mean, I know I'm fine as long as I'm sampling the signal with less than 5 millisecond intervals. That's my sampling period, 0.5 milliseconds. Then let's say, of course, Fs would be 2 kilohertz, right? I need to calculate my omega 0 hat, normalized frequency. I know my omega 0 hat is omega ts, which is really equal to 200 pi. Just take omega 0 here. 200 pi times 0.5 time to the minus, maybe let's just write it 5 to the 10 minus 4, which is 0.1 pi radians. Okay? This can be also written as 2 pi times 0.05 radians. Okay, so I have x of n, so the first sampled signal, I mean sampled signal, not the first, sampled signal at this sampling frequency is cosine, actually 0.1 pi n, or equivalently cosine 2 pi 0. Okay, this is it. So from here, we could look at the fundamental period. Remember, we were looking at this ratio, and we're trying to pick an integer from there. Okay? What is it? It's 2 pi 0.05 over 2 pi k over n. Maybe this is 1. Let's pick it as 1. Actually, I'm trying to go to n here, pick an n. 1 over 0.05, which is 20. So I can say my fundamental period is capital N is 20. I want to know AK. What are the Fourier series coefficients? Okay. We want to calculate these guys. Apply our definition. Okay. So let's go. AK 1 over n, which is 20. I can go from k0, or sorry, n time. I'm summing or integrating over the time variable here because k is still my variable. X of n, e to the minus j. Now my bases are, remember, 2 pi over n k times n. Okay? So remember also, recall, I know AK plus 20 will be equal to AK, right? This is also something we know. All right. So now let's continue. I mean, normally you would have to go through this, but here this is a cosine. Guys, when I have a signal that's written in terms of summation of cosines and sines, it's not wise to use the Fourier series formula. So do not use, I can say note, if I were you, I would not use this Fourier series analysis formula here. This is the Fourier series analysis formula. Analysis equation here. Why? I have already cosine expression because I can really expand this cosine into the basis functions, right? Complex exponentials through my Euler formula. So let's do that on the next page. So it's really x of n. Remember, it was cosine 0.1 pi n. This is really equal to 1 over 2 e to the j 0.1 pi n plus 1 over 2 e to the minus j 0.1 pi n. This is important, okay? So you see, this is really like, I mean, I wrote this analysis integral so you see which terms are non-zero. I have 20 terms. unique terms, and they repeat also every 20, right? So here exofan, there is A0 plus A1. Now I'm opening this analysis, by the way, this one, this analysis formula, from the analysis formula. Just open it up, expand it up. Just currently I'm writing it. A1, what is it? Put k equals 1, e to the plus minus j, j 2 pi over 20 n plus a2 e to the j. Actually, here I need, okay, 4 pi n over 20. Now let's see, a3 e to the j 6 pi over 20 n. All the way to plus, for instance, a18 e to the j 2 pi over 20 18n plus a19 e to the j 2 pi over 20 19n, right, from the formula actually. Now we just read off, I mean, this is really, let me rewrite it maybe for your notes. Exofan is actually synthesis formula, right? Sorry, I wrote it analysis, but actually used from the synthesis formula, guys. From the synthesis formula. Okay, so which is here actually. So let's maybe do this. Yes, k0 to n minus 1 here, which is 19. Okay, ak, because I need to do the forward transform here. I mean, I'm trying to see in this cosine which of these AKs exist. That is what I'm trying to do. E to the j 2 pi over 20 kn. Okay, this would be the synthesis formula, and this is what we have written up here. So from here we can just see I have A1, guys, right here is 1 over 2, and I have a minus 1. This is actually a minus 1. This is a1, and I know a minus 1 is equal to a19, right? Because it is a minus 1 plus 20. So that is really this guy. That is then giving me actually which AK I have there. Let me just note it again. K over n, which is 20. Okay, maybe let's write it as 20. 20. This is in the index, so let me write it so you don't really get confused. Is AK, these are what we know, and we just found out A1 is 1 over 2, and A19, or which is A minus 1, is 1 over 2. And all others are 0. 0, A2, A3, A4, I mean, that's A18 are 0, and also their minuses and stuff, right? And plus 20 versions. So these are the Fourier series coefficients of this signal. Let's plot it. Yes, let's show the spectrum. So what is the spectrum? Remember, it's the frequency spectrum, right? Then what is it? Spectrum of exofan is really, let's plot an axis line here. K is our frequency variable now, remember, right? In the spectrum, in the Fourier basis, I can always write a K here. There is a 0 axis, let's write. I have plus minus 1 here, 1 and minus 1, by the way. They are 1 over 2. Okay. And then I need all these 0, 2, minus 2, 3, minus 3. I need to just do at this guy. Let's say I have a 19, which is again, of course, 1 over 2. 20 is 0. And 21 is again 1 over 2, right? 1 plus 20. Okay. Minus the same, do the same here. Minus 19, minus 20, minus 21. So I need to also have 0 and this guy. 2, 1 over 2. You see, there is a repetition here. There is periodicity, you can see. I need to only look at, we can just take, we just look at one period. So in frequency domain also, for discrete time signals, you see already for periodic signals, it's enough to look at one period, right, in the time domain. We just look at in frequency domain too, which is good. So because we know AK plus here 20 is AK, okay? And it's gonna be repeating itself every 20 of these. So if you just take a 20 period here, for instance, 0 to 19, this pattern repeats. Or you can take any 20 periods. Is there a question, guys? Yeah, this is, thanks for the question. This is special case. It's not always, yeah, I mean, because there is only a single sinusoid here, okay? Good question. Now I'll do a version with later multiple sinusoids. We will have multiple of those, okay? Yes, good question. This was, but guys, look at this case here. Sorry. The form of the spectrum changes with respect to the sampling frequency. So now, for instance, let me see. It was repeating every 20. Now change the sampling frequency. Now sample at the second case. This was first case, remember? We sampled at TS 0.9. Now do this one. Now do this to sample it. Now sample the same signal. No, with at, let's say, TS is 2 milliseconds. Remember our constraint, we need for a proper actually sampling, we need TS less than 5 milliseconds. Okay, 2 milliseconds. This was 0.5 here. Now it's 2 milliseconds, which is fine with respect to the sampling theorem. Sampling constraint in a way, right? Constraint. Okay, so this is really sampling frequency then is 1 over TS, so 500 Hertz. I have my signal, the new discrete time signal, you see, is different. It's cosine 2 pi. You see, because the way we sample a continuous time signal, things change, right? We're taking samples from different parts of the signal. 2 pi, 100 to 10 to the minus 3, n. Here, I just inserted omega 0 hat, by the way, guys. Omega 0 was 2 pi times 100. Recall, this is not. This was the original signal, right? This is my omega 0, 100. In omega 0, two things. 2 pi 100, so 200 pi. I brought it here. Now I need to find my normalized frequency. This is really omega 0 over Fs or omega 0 times Ts. Normalize it. Maybe it's easier to remember it this way. It's up to you guys. So it's really then, let me write the result. It was this guy, 100 times, because it's 2 pi 100 over 500 Hertz, which is equal to 2 times 10 minus 3. The 2 times 10 to the power minus 3. Now, that's why I have this cosine, discrete time sinusoid. We obtain, let's say, with this sampling. Okay? As a result of this same continuous time signal. The continuous time signal was sampled here. Okay? So now we can do the math again. Guys, here on this side, let me do it. What do I have? This is, I think, 0.4 pi, right? 0.4 pi. So it's really cosine 0.4 pi n. Okay? Can just check it exactly. Okay. So I need to check, remember, whether to see this is a rational number, 0.4 pi over 2 pi, right? Is this k over n? I think I can pick n equals 5 in this case. Yeah. Pick. I have sampling period. The smallest possible capital N here. It's 5. Now this is important. To define this is important. I go to my Fourier series representation of the signal. Fourier series representation of the signal of x of n becomes, because that capital N is used in its form, remember it's k0 to n minus 1, it's 4. Now, this is n minus 1, remember, ak, and also it defines my Fourier basis, okay? Defines the Fourier series basis function. So e to the j 2 pi over 5kn, okay? That's the Fourier basis here. This is important. Complex exponential. And one other thing I know is ak plus 5 is ak. So from here also, I know it's enough to calculate a0, a1, a2, a3, and a4. Okay? Just calculate these. Everybody else will come from these. Just calculate these. That's enough. Okay? So let's plot the spectrum. Or first, okay, first let's maybe derive or so question, or what is the spectrum, or plot the spectrum, find and plot. Then plot the spectrum of x of n in this case. Okay? Then in this case meaning in this sampling, after this specific sampling frequency. Now, x of n was cosine 0.4 pi n. Just use the Euler formula. I told you you should really memorize this guy. 2 pi over 5. Remember, this is my basis function plus 1 over 2 e to the minus j 2 pi over 5n. Okay, so which ak do I have here is important. Now let's look. I mean, again, I know that this can be written as, I think you guys will say a1 and a minus 1, but it's fine. I'll just write it again openly, because you can see the basis, corresponding basis, plus a2. If you find these other bases, then they have their coefficients, otherwise they are 0. And plus a4, remember a4 until a4 is enough, otherwise it's going to start repeating itself. So which ak? So I know also from the synthesis formula they are equal. Which ak question is, which ak do I have? You guys will immediately say, hey, I have a1 is 1 over 2. This time you see, before it was a minus 1 equal to a19. Now it's equal to a4, right? Because it's a minus 1 plus 5. Okay, so that's equal to 1 over 2. Now the spectrum of x of n. Remember, spectrum, why do we care about it? It's a compact way to represent the frequency content of a signal. It's not easy to see it looking at the time domain representation. That's why we know or learn how to move between time domain and frequency domain representation of signals. Again, k, our frequency variable. Remember, this is our frequency domain variable. Okay, 0. Now I need to put down again 1 over 2 and minus, 1 over 2 at minus 1. And we should just repeat these at 4. 5 is 0. Then repetition comes. 5 is 0, but now 6 is 1 over 2, because a 1 plus 5 is a 6 is also 1 over 2, okay? The periodic repetitions start after some point, 8, 9. Then 9 is actually again 1 over 2. 10 is 0, 11. Maybe I should really make this, write this. I mean, this is k, frequency variable. 10 is 0, 11 is again 1 over 2. Just for your notes when studying, this is 11. K is the frequency variable. I do the same for this side, guys. And I mean, you guys can just check this guy. AKR periodic is the keyword here. Okay, AK periodic. This is what we're looking at is the spectrum of exophan. So we can really look at n of these. AK are periodic, so n AK, looking at n AK are enough. Is enough, of course. Is enough. So I could really say, by the way, this was a mistake. I mean, you see, the same thing holds, by the way, this symmetric view, two-sided spectrum still holds for a real signal, but there will be conjugate symmetry. These are now currently cosines, so the AK were real. I'm going to give a sine example, so we see also conjugate symmetry in the coefficients, okay? Looking at n AK, sorry. N of AK, let's say, because you may just think n of AK is enough. So we can view only one period. For instance, we could view just 0, 1, 2, 3, 4. This would be one of them we could see, or we could see any actually. Just take 5 samples for instance. I mean, just take 5 samples. You could really come up with 5 samples. Any of them are fine. Because it's going to repeat itself, right? So this is now you see how things also tie back to the continuous time signal. Now I'm going to give another example. This is an exercise for you, by the way. The spectrum may look a little bit different. Just guys, we've done okay already. All right, so let's give you an exercise. I'm gonna give you the result too, so you guys can do this. Now I'll give you a single sign, exophan, and then I'm gonna solve for multiple sine cosines again, just to really solidify this for discrete time Fourier series coefficients. Sine 6 pi over n. This is really like sine 6 pi, 2 pi. You can view this, by the way, as 2 pi over n, some n times n. Okay? So I'm asking you, calculate and plot spectrum of exophan. So here you need to calculate AK. Maybe I'll give you a hint. Look at this guy again, okay, to see the periodicity and the fundamental period. Any questions here? Ali, are you guys tired? Do you need to give a break now, or how do we do it? Sali asks, are we going to have a break before the quiz? It's up to you guys. If you guys are really tired, because now it's an hour. I think we started at 9:50. It's up to you guys. Yeah, I realized a break would be good. Okay, it's too much, I know. Okay, give a 10-minute break. See you at 11. Then we do 15 minutes more and you guys go to a quiz. Okay, see you soon after 10 minutes. All right, so let's complete a few more examples for you to be able to understand how to really go from the discrete time signal to the Fourier domain, which is through discrete time periodic signal, I have to say. Now it has to be through Fourier series, discrete time Fourier series. I think before the break, we just left with this example. And this is an exercise, but just for you not to get really too confused, here you can say, you see it was 6 pi over n, but it's 2 pi over n, k n type. So it's really n is 5. You can think of k is 3. So if I ask you what are AK for this signal, question was what are Fourier series and plot the spectrum. What are the Fourier series coefficients and plot spectrum? You have to find, for instance, I'll give you a hint. A3 is 1 over 2j. Okay? This is equal to, because n is 5, also a minus 2, for instance, or equals to a8. Okay? And I know a minus 3 is minus 1 over 2j for a sign. Now, you have to just go to the plus 5, a2, plus a7, etc. Please plot the spectrum also, okay? I already gave most of the answer, but you can just solve this on your own as an exercise. Here is one more example. This could also actually go as an exercise. Let me write the example. We start with it. I think it will be easy for you to complete this. So there is, this time you see a constant term, which is a0. You guys know this already. Sine 2 pi over n plus 3 cosine 4. Okay, it was also 2 pi over n plus cosine 4 pi over n plus pi over 2, for instance. Now, first of all, just see, let's say this is omega 0 hat, right? And I have 2 omega 0 hats here, right? The fundamental frequency, but normalized frequency. The question is calculate, okay, discrete time Fourier series coefficients for x of n. Here you see you have to start with asking what is the fundamental period. It's n here, I mean given as symbolic, so it's fine. Now x of n is really just expanded by Euler expansion. Let me give you this and leave it up to you. Then 1 over 2j. We've already actually shown an example like this before, but e to the minus j 2 pi over n plus 3 over 2. But here you will see you have to add some of the terms, right? Bring them together. 2 pi over n plus 3 over 2 e to the minus j 2 pi over n. Then I need plus 1 over 2 e to the j pi over 2 is the phasor or coefficient part times the third cosine. I'm at the third cosine now, right? 4 pi over n plus 1 over 2 e to the minus j pi over 2 e to the minus j 4 pi over n. Okay, so just write from here, for instance, I mean just determine the Fourier series coefficients here, okay? So just a sec. Okay, A0, I have A0. I have for these guys together A1. These are together A1 plus, of course, right? A minus 1, this one, and this one, A minus 1 added together, and this is A2. Again, this is A2 and A minus 2. You see, you can really spot which frequencies are there and which coefficients are there. Omega 0 hat here was already, the fundamental frequency was 2 pi over n. A0, so you have to write A0, one is this guy. Okay, A1 here, I think maybe let me write this, is 1 over 2j plus 3 over 2. For this guy, you have to really do the math a little bit from here. For instance, what is the magnitude of A1? And you should find the angle of A1. I mean, it's on the complex plane, right? Real is 1 over 2 and, sorry, real is 3 over 2. The imaginary part is j over 2. Right? J goes up, right? This is minus j over 2. Sorry, I'm looking at the other way around. Let's just maybe do it in this way. J, right? 1 over j is actually, j goes up as minus j. So I have really, I can draw it in this way. Real part is 3 over 2. This is the imaginary axis, remember. This is minus j over 2. You have to have here the magnitude. So you see this is really magnitude A1, which is whatever sum, it's actually square root 10 over 2. The angle of the A1 will be arctangent. You guys should just see this from the plot, minus 1 over 3, right? You can calculate this. Is this clear? A1 was plus 1 over 2j. Sinan, A minus 1 is minus 1 over 2j. That will become the other, yeah, exactly. A minus 1 here is A equal to A n minus 1. 3 over 2 minus 1 over 2j, which is 3 over 2 plus 1 over plus j over 2. For this guy, you have to go j over 2 and 3 over 2, okay? That's the difference. So here then, this will be a minus 1, okay? Is it clear now? Okay, yes, good. You guys see what's happening here. Then I should also write A2 itself is 1 over 2 e to the j pi over 2. Minus 2 is a n minus 2 also equal to the same thing. By the way, guys, these are real signals, right? I have to note, this is important. Note, this is an important note. I mean, from before you know it, I won't be deriving again because we derived it, I think, last week for the continuous case. It's the same typical derivation. I mean, for real signals, remember, we write the synthesis equation, take the complex conjugate, and because it's a real signal, we equate both sides. Salih, yes, if it's a sign, but it could have come with a minus in the beginning. Don't memorize. If it was the first x of n was 1 minus sign, then like you said, it would be a1 would have minus 1 over 2j, which would be this other one, the second coefficient, okay? So there could be in the equation of the signal, it could be a subtraction. Yes, great. It's good to ask these questions. Perfect. So this is, by the way, for recall, I should say, we did this for, if you forget this, check your continuous time Fourier series derivation. Remember, for real signals, like I said, we started with the signal representation, take a complex conjugate, and we arrived at the fact that the complex conjugate of the coefficient is equal to the negative index coefficient itself. This is valid only for real signals. We derived it for real signals. Check your derivation, okay? If you guys forget this, but it's also, you can see valid here. Let me show it on the spectrum. This is, I think, may look a little bit complicated. So let's pick a capital N to show on the spectrum. Let's pick n equals, this is pick n equals 10. I mean, this is because I've given the general form of the equation with the capital N's. I mean, this was capital N, by the way. Okay, now let's pick 10. This is given, I mean, by construction. This is picked or given. Now plot the spectrum, because I already know which AKs are there, which coefficients. Plot the spectrum, meaning we are looking at the frequency domain representation of this signal. Okay. K. And I think probably this will be the last example we will do. It's 11:10. So guys, let's see. Where is the center? So let's say this is 0. I think we had a 1 here. Right? A0 was 9, exactly. Just read off from there. This is really A0. Now I want to bring A1 and A2, A1 and A minus 1. They will be complex conjugates of each other. So you see, A1 was from here. Maybe let's write it. E to the minus plus j, let's say, arctangent minus 1 over 3. I mean, I didn't pick that or just calculated that, but this is our A1. We know this is equal to A minus 1 conjugate, or its conjugate is equal to A minus 1. So we can bring it here. So for this guy, I can use a different color. Let's make it, because it was square root 10 over 2. Let's say this was A1, which is this guy. We already calculated this. To the j, arctangent minus 1 over 3. Now I know A minus 1 is the complex conjugate of this guy. Let's make it by another color. A minus 1 is really then e to the minus j arctangent minus 1 over 3, you guys. And it's a plus, right? I could have taken it inside. So let's maybe make it a plus. You can check the math here if you want. This is meaning this is really equal to A1 conjugate, right? Exactly. Now go to the, this was a, these are guys 1 minus 1. Let's do this 2. I should do 5. I think 10. Okay, I need 10 here. These will replicate at 10, 11, 12. So that's why I did, okay, this is important. Also minus 2, we will draw minus 3, minus 4, etc. Let's go all the way to, okay, maybe minus 5 and go to minus 10. Here, dot, 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 minus 10, right? Okay, what did I do here? It's a funny thing I did. Sorry for this. It should be, guys, sorry. It should be one more. Let's see, centered around 10 because it's periodic with 10, right? So let's pick this as here. So 10, 11, 12, 9, yes, 8. Okay. And the same thing here, minus 10. Then I need really 9 and minus 8. Guys, 11, minus 11, minus 12. Okay. So let me complete, by the way, minus 2 and 2. These guys were A2 was 1 over 2 e to the j pi over 2. A minus 2 is really A 1 over 2 j pi over 2. Okay. So this pattern will repeat every 10 samples. Okay. So at 10 minus 10, we will have the same pattern. So actually at, for instance, 8 and 12, I will have these guys. A8 is equal to A minus 2. This will be equal to A12 is equal to A2. Okay, now let's go again to the green, which is 9. This is equal to A9, which is equal to A minus 1. The centerpiece is the same. This A0 repeats at A10, right? A10 is A0 really, which is 1. And then I have A1 at A11. A1. Okay. So, and also replicates on the other side, by the way. The same pattern, I should have probably drawn it, replicating here, right? Here. here and here, and then I need the center guy, the final piece here. Okay, I mean replicates. So it's fine to look at this, for instance, between -5 to 4, let's say, or it's fine to look at this pattern between 0 to 9, of course. Replicates and replicates. Of course, replicates even in both directions more. But so AK should be only AK from K0 to 9 are unique, then replicates, of course. But I can look at it in any period. So next time, we will look at discrete time Fourier series for things like, for instance, what we call periodic square wave. Then we will have something called periodic impulse train. And we can look at some of the textbook slides, which are also very nice graphically for illustration, and finish this up to go to systems. Next time we start systems after we finish this. But this is, I believe, this discrete time Fourier series a little bit more, not complicated, but may look a little bit confusing than the continuous time version because of this replication business. But I mean, it's periodic. Now AKs are periodic, but just try to understand the fundamentals of it going through the notes. And we can tell you where to read in the lecture notes. Let's see if our assistants are here. I can leave the floor to them now. Any questions, guys? I think this is enough for today, and you have your quiz time. So, but I think we've solved enough questions, so you have enough problems. Now, I think if you can at least go over these, we've mainly solved problems with cosine sine components already, but like I said, next time I'll solve you more general other sequences I mentioned, for instance, a square pulse or an impulse sequence, so we can then move on. All right, so let's go to the quiz now. I'm stopping the recording.